global climates, mitigation of climate change. We're going to look now at the potential mitigation strategies of climate change on a global level. Okay, and climate change is a global commons problem. It's now the commonly held view that climate change mitigation is going to need the involvement of all governments and all societies around the world. Now, in this lecture, I'm making use of a number of the IPCC documentation. The IPCC, the Intergovernmental Panel on Climate Change, makes all of their information freely available because they want the information to be disseminated around the world. This is the new report, which has just recently been published, Mitigation of Climate Change. If you go to the IPCC website, all of these documents are downloadable. They are very, very large documents, which is why I've extracted some of the key information. Okay, so that's what's in the document. And as I say, the evidence is freely available. So this is the IPCC database of the scientific evidence. Now, it's incredibly complicated, but you can go in, you can look through all of the different scenarios, different sectors, different countries, and all of the data that they are using is held on that database. Now, for us, it's too complex. We wouldn't need to use it. But the important point about this is that the information is being made available to the whole world so that anybody can verify or check scientific basis. And the argument now is that the scientific evidence is so strong that governments cannot fail to act for the reason that they have doubts about the evidence. So the view now that's being proposed by the IPCC is that governments must act because the evidence is so strong. This is the kind of contribution to the report. Many, many people around the world, many experts, thousands of people commenting, a huge global effort to verify the information. So, there is far more carbon in the ground than emitted in any baseline scenario. So if we look here, we've got the projected carbon stocks, gas, oil and coal. There is a huge amount in the ground. The question is, can we afford to access it? So GHG means greenhouse gas. So greenhouse gas emissions growth has accelerated despite reduction efforts. So at a period when we need to be reducing greenhouse gas emissions, over the previous years it's actually been accelerated. And the greenhouse gas emissions growth between 2000 and 2010 has been larger than in the previous 3 decades. So the graph here is the total greenhouse gas emissions for the whole planet. And as you can see, the emissions are getting greater and greater at a period when we need to be reducing them. Okay, and that's some of the kind of increases that we've seen. When they talk about uncertainty, what the IPCC do is the evidence is always qualified by giving you the kind of range of certainty. So they're very honest about it. So in this case, they're saying that the 49 gigatons of greenhouse gas emissions per year is within 4.5 plus or minus. Okay. About half of the cumulative anthropogenic CO2 emissions between 1750 and 2010 have occurred in the last 40 years. Anthropogenic means due to the operations of mankind. Okay? So, in other words, in the last 40 years, we have started producing huge amounts of CO2 emissions compared to the previous 140, 130 years. And regional patterns of greenhouse gas emissions are shifting along with changes in the world economy. So what we've got here is a breakdown looking at 1970, 2010, and looking at the breakdown of the emissions in terms of land use, industry, buildings, transport, energy, across different income economic sectors. So, probably unsurprisingly, the high income sectors have been producing more greenhouse gas emissions than the lower income sectors. But the trend is that it is increasing. And you can see the breakdown here that energy is a huge factor, transport is a huge factor, and buildings are quite a significant factor. Just bear with me a second. Can you turn the music off, please? I've got a lecture. Thank you. Okay. Greenhouse gas emissions rise with the growth in gross domestic product and population. The long-standing trend of decarbonisation of energy has been reversed. So what we're looking at here is the light blue is the change in greenhouse gas emissions due to population change. And what you can see is that it's relatively flat. Okay? So the increase in greenhouse gas emissions over the past 30 to 40 years is not a significant result of population change. And often that's a misquoted fact that we're producing more carbon dioxide because we have more people in the world, but it's not correct. What we are seeing is that the greenhouse gas emissions are increasing due to gross domestic product. So to do with economic increase. And the decarbonisation, what we mean by that is the processes that are actually reversing the greenhouse gas emissions, such as planting trees or carbon capture, which were previously increasing, have started decreasing again. Okay. And you see what the arrow is pointing to there is that the improvements in carbon intensity of energy, which were previously negative and improving in the last 10 years, are now resulting in an increase. And a key fact, limiting warming to 2 degrees centigrade involves substantial technological, economic, and institutional challenges. We talk about limiting global warming increase to 2 degrees. That will happen. We are absolutely certain now we are facing at least a 2 degree global warming over the next 100 years. It's too late to do anything about that. What the mitigation measures are now aiming at are limiting that global warming to no more than 2 degrees. And without additional mitigation, the global mean surface temperature is projected to increase by 3.7 to 4.8 degrees centigrade over this century. So that is, that's what we're facing unless we can increase the mitigation. Okay? And what we're looking at in the graph here is the level of additional risk due to climate change, from very low risk through to very high risk. Here's our temperature increase, and it's quite a simple diagram, but what you can see, in simple terms, the higher the global warming, the increased risk to threaten systems, extreme weather events, distribution of impacts, global aggregate impacts, and large-scale singular events. So this is the sort of very common graph that you will now see from the IPCC, which is looking about stabilization of atmospheric concentrations. Okay, and we're looking at the annual greenhouse gas emissions globally over this century. So the baseline is the dotted black line, and this the red line is the sort of median. If we continue as we are, we'll be increasing our greenhouse gas emissions. What we then need to look at is what are called the scenarios for reduced greenhouse gas emissions. And the IPCC looks at a number of scenarios. So they're looking at what happens if we do nothing, what happens if we reduce by this amount, what happens if we reduce by smaller amounts. And they talk about these in terms of concentration levels. So we're talking about ppm, that's parts per million, of carbon dioxide in the atmosphere. And clearly, what we're talking about is to limit global warming to 2 degrees. We need to limit the concentration levels to 430 to 480 parts per million. And our annual greenhouse gas emissions needs to drop significantly over the century. So, mitigation involves substantial upscaling of low carbon energy. We cannot achieve this unless we start increasing our low carbon energy production. Okay, and that's what this graph is really just trying to say. Comparing that, so we've got 2 examples here. What we're looking at is, this is our best scenario, our 2 degree scenario, and this is our 3 degree scenario. And this is the percentage of low carbon energy that we'll need to be producing. So in our preferred scenario, by 2100, we need to be producing virtually all of our energy from low carbon sources. For the 3 degree scenario, we need to be producing about 70% of our energy from low carbon systems. Delaying mitigation increases the difficulty and narrows the options for limiting warming to 2 degrees. So the message is we need immediate action. And what we're seeing here is this idea that we peak the greenhouse gas emissions now and we start to drop it immediately. Okay? So, looking at the rate of change, we need to start rapidly reducing our CO2 emissions going forward. Okay? And the shares of the low carbon energy, as we've just seen, need to move up so that most of our energy is low carbon. Okay, we'll talk about that. Mitigation cost estimates vary, but do not strongly affect global GDP growth. So the figure that is being quoted is that the cost of greenhouse gas emission mitigation is 0.06% of global GDP. Okay, so 0.06%, so quite a small figure in a way. And the global costs rise with the ambition of the mitigation goal. So if we look at our most ambitious scenario, 450 parts per million, okay, then over time, the reduction in consumption relative to the baseline has to be greater, okay. So as you'd expect in a way, that the most successful scenarios will have a greater cost in terms of gross domestic product. And I think this is a very interesting slide. The availability of technology can greatly influence mitigation costs. So what we're looking at here is we're looking at some different technologies. So we've got no carbon dioxide and we've got capture and storage. So capture and storage, in other words, technologies that allow you to capture the greenhouse gases and store them, lock them away so they don't make it into the atmosphere. Here we've got the nuclear phase out, here we've got solar and wind, and here we've got bioenergy. And we're looking at our two scenarios. The orange is our 3-degree scenario, the blue is our 2-degree scenario. Okay? And we're looking at the increase in mitigation cost relative to default technology assumptions. So it's quite a complex graph this, but what we're saying is, if we do not find technologies to provide carbon capture and storage, then the cost to the planet will be much, much greater. If we fail to find technologies to produce bioenergy, again, the cost will be greater, but not as great. So, in other words, we are relying on developing the technologies for carbon capture. It's very much seen as one of the most successful ways that we will meet the mitigation targets. And mitigation can result in large co-benefits for human health and other societal goals. So, in other words, quite simply really, what they're saying is that some of these mitigation strategies will have other benefits. So moving to cleaner, low-carbon energy sources will also result in a reduction in air pollutants. So there are kind of cross-cutting benefits there. This is looking globally at the air pollutant ranges across the planet, and what the graph here is saying is that there can be a significant improvement through low-carbon technologies. Okay, low stabilization scenarios are dependent upon a full decarbonisation of energy supply in the long term. So we've already said that, but basically, if we want to limit global warming to 2 degrees C, we need, by the end of this century, to be producing energy without any carbon. Okay, so looking now at the the rise in greenhouse gas emissions in all sectors. So, let's look at the ones that are interesting to us. We've got buildings here. Okay. Predicting an increase in greenhouse gas emissions, but not nearly as great as the electricity production, not as great as industry, not as great as transport, but still significant. And if we look at our 2-degree scenario, we look at buildings again, we need to be reducing our carbon emissions very close to zero. Okay? The electricity production has to go into the negative carbon. So in other words, carbon capture. So the previous slide is with carbon capture. Okay, and then without carbon capture, because we're not capturing that carbon, the situation is very different. I know there's quite a lot of complex graphs here, but you'll have to re-watch it and have a look at it yourself. Okay. So, as we've said, decarbonisation of the energy supply is essential. Okay. And if we look at the supply of primary energy in 2050, coal with carbon capture, gas with carbon capture, nuclear, biomass without carbon capture, biomass with carbon capture, solar, wind, geothermal and hydro. Okay, we've got high energy demand and the low energy demand. And this is giving us a feel for the kind of distribution of where that energy may come from. Okay? So, reducing energy demand through efficiency enhancements and behavioural changes are a key mitigation strategy. And we look again at transport, buildings and industry. Okay, and again we're looking at the 2 relevant scenarios, the 3-degree scenario in orange and the 2-degree scenario in blue. Sorry, let's go back there. Okay, I'm looking at the final energy demand reduction relative to the baseline. And what you can see is we are looking for this reduction, certainly in buildings, especially in transport, we're looking for this significant reduction. The wide-scale application of available best practice low greenhouse gas technologies could lead to substantial emission reductions. So there is a kind of optimism that the technologies that we are researching now and that we are developing could lead to successful mitigation. Okay. So many technologies exist to reduce greenhouse gas emissions, but to different degrees. So if we look at some of the different energy sources here, solar photovoltaic, biomass, coal with carbon capture, nuclear, wind, gas, hydroelectric, and coal without any carbon capture. Okay, if we look at the emission intensity of these different energy sources, standing out as the worst is coal in terms of the greenhouse gas emissions to produce the energy. Okay, coal, clearly the worst. Gas is next. And then we move into a much closer band with hydropower spread across quite a large range, but with quite a low median value. Biomass reasonably high. And we're left with photovoltaic, nuclear, and wind as some of the best performing energy sources. And And then this is a comparison in terms of the cost. Okay, and it's kind of interesting that some of the worst performing energy sources in terms of greenhouse gas emissions are unfortunately the cheapest energy sources. And this is the problem we're faced with, that some of these much better energy sources, such as wind or photovoltaic, unfortunately cost more to produce at the moment. So, if we look at the example of transport, there are several strategies that exist to reduce emissions from transportation. So at the moment we've got gasoline, hybrid gasoline, electric. That's now in 2030 gasoline, hybrid gasoline biofuel, and kind of clean electric. Okay? And you can see the different sort of intensities of emissions. So this is how much carbon do we produce per energy unit. And as you might expect, gasoline, in other words petrol, is the sort of biggest producer of greenhouse gas. And the cleaner technologies down here are releasing much smaller emissions into the atmosphere. Okay, and then again, comparing the cost, we're not even looking at gasoline here because I think the belief is that gasoline is just not going to be an option. Okay, but looking at the cost, there are these costs associated with these cleaner transport systems, but not unsurmountable. And effective mitigation will not be achieved if individual agents advance their own interests independently. So the message very much from the IPCC is that governments need to work collectively. It will not work if we're trying to work independently. And yet, substantial reductions in emissions would require large changes in investment patterns and appropriate policies. Okay. There's been a considerable increase in national and sub-national mitigation policies since the previous report. So if we look here, 2007, 55% of the planet had no climate legislation. 2012, only about 30% of the planet has zero climate change legislation, with large parts of the world now imposing some level of climate change legislation. So it's a positive message. Okay. And then just briefly, before we finish, we've got a quick video to watch at the end. Greenhouse gases by sector. So we've seen this already, but it's just a reminder that buildings, 6.4% here, 12% here, so that's 18%. Transport, 14% here, plus about 3%. So these are the things that we can influence as designers. So collectively, if we put buildings and transport together, we have a significant proportion of greenhouse gas emissions that we can influence. And this is looking at the global energy consumption per capita across the world, and not surprisingly, North America is using more energy per person, with parts of Asia, China, using much lower rates of energy per person. Okay, so there's a kind of global inequality there. This is the projected residential and commercial energy use. Okay, you can look at this in your own time, but looking across the different regions, just analysing that some areas of the world were predicting a sort of level consumption, and other areas were predicting, increases. And here we're looking at some of the different scenarios. So we're comparing blue, which is the historic energy use, yellow, which is the difference from state-of-the-art to moderate, and green being the sort of state-of-the-art energy systems. And what we're just looking at here is across the globe, what proportion of those energy systems will we need to use? Yeah, climate change mitigation is a global commons problem that requires international cooperation across scales. So it's just repeating that message. It requires governments of the world to work together. Now we're going to watch a 10-minute video which is just looking at some of the mitigation principles.